if you check archive, you see that there is a little bit decline in activity in the last year, and everybody knows why. So the question was, shall we, stop any activity or try to force actually activity? And this meeting came to not to stop activity, to promote activity with all the difficulties of online meeting and different time zones, and we are aware of everything and high constraints of different people from different places like universities, people who start to teach, and people who had other difficulties because of the times and so on. But we decided not to stop the activity. And some other meetings I'm also involved in. I think the direction should be that we should have online meetings with the aim of having in 2 or 3 years another meeting where somewhere where we all can meet again as usual. Some people will not come and we will connect to them by Zoom. So this is a basic goal of this meeting, to promote some activity and, to discuss. So we have lots of discussion time. We must have it in online meetings because we don't have the coffee break and dinners and so on. So I welcome all of you, many young people here who didn't finish their PhD yet, very welcome. Some of you, this is the first meeting. And especially I would like to welcome somebody who submitted his PhD, I think in the summer, but it was in 1971. So I'm not sure if it was in the summer or the fall, I don't know. Bruce, I'm so happy to see you here. 50 years since you submitted your PhD, you don't remember it. I tell you about historical, and I'm very happy to see you here because, this gives a continuation to our community, and I'm very happy to see you here as well as young people here and some people in between the young people and Bruce, like me. So, yeah.
No, thank you very much. Any day above ground is a great day. Thank you.
You're welcome, yes. And you have a nice background, yes, Bruce. I will not ask you about the shaping mechanism. This also I might do. So, so we have some other meetings that you might find relevant in the coming months, like I'm involved in Outflow for Involved Stars and in Planetary Nebulae meeting. And there are other meetings. You're welcome to join all these meetings. So I think we will start now, and I will start the recording now. And actually it was, okay, it's already active. Thank you very much for activating it. Ursula, please.
Okay, so sharing away. No, I can't see anything anymore. Okay, just shout if you don't see the screen. Okay, so I am supposed to kind of give some talk that sets the stage and poses some questions. And I decided to, I'm not going to be very long. I'm just going to be about half an hour. And then we'll have a little bit of time if the session chairs want to add anything to those questions. But the important thing is that we have a little bit of a data bank. I already posted a preliminary list on the Slack. And then that these questions, or part of them, get mulled over by you, and hopefully get some partial answers during the talks that we'll be listening to. So we all know the paper by Baczynski in 76, okay? It laid out this beautiful scenario to explain why there are these binaries that are evolved, and the orbits are tiny, but the binaries precursors were much bigger than the orbit. And if you read that paper, it makes so much sense, and it's so beautiful and actually so easy to understand. But of course, as time went by, we're starting realizing there's a lot of details in this apparently simple picture that need to be explained and actually are causing a lot of grief at the moment. So just a little instruction for use. Each of you works in some aspect of or related to common envelope interaction. So find yourself, if you can, within the slides and post in the channel, in the intro channel, any thoughts you might have, whether you agree or disagree, there's anything I missed or whatever you think is important and wasn't in here. And this, I will try tomorrow when I get up to gather some of these questions and discuss with the session chairs how they can be used for the discussions in those sessions. So the questions are in red and they're summarized at the end of the talk, and I will repost them in the Slack. So I made some changes. So I've organized this little outline in 3 blocks. The first one is 4 topics we all think about and are giving us, keeping us up at night. And then I have 2 blocks, one on observations, one on theory. It's kind of a bit of a request of observers or theorists, but also try and consider what we really, what are the problems in those 2 domains. So at first I thought, okay, before we start, let's have a little bit of a timeline of the common envelope. We all know what it is. You have pre-common envelope and your end spiral and your post. And there's been many, many papers and reviews that have given detail about what might happen in all the various stages leading to the end spiral and then eventually after the end spiral if a binary survives. But I wanted to remind you of it because even as I was writing this wasn't supposed to be questions. Questions were just bunching up, and Paul sent me some questions and they all pertain to this timeline. So we know we have a time when the binary is just not doing anything. They're separated, they're not evolved yet, but eventually something happens. Usually one of the 2 stars evolves and grows, and within some kind of tidal time scales, you end up at the Roche-Lobe overflow. Now here, you might have some you might have some thermal timescale Roche-Lobe overflow, which is somewhat stable, but clearly, if you're going to go into common envelope, you're going to have some time of instability, which we call the common envelope onset. So this is kind of tightening and shortening time scales that eventually lead to the end spiral. But here, there's tons and tons of juice to be drunk, to be mined. What systems enter the common envelopes and which ones do avoid it? So not the clean cut, obviously these are the stable binaries and this will go into common envelope, but there's a lot of stuff in between. When the binary ratio becomes kind of similar, and maybe when one star is very big and very convective, at that point, you know that you're not going to avoid it. But there's a lot of the systems where, to be honest, we might not know exactly whether they will avoid it or not. What determines that speed of the onset? In simulation, we see a quickening lead up to the end spiral. We know simulations are not giving us that speed correctly, but what is that speed? Now, there's been a couple of papers recently, and I even wrote a paper a long time ago about elliptical common envelopes, elliptical orbits. And Paul actually asked the other day over email, can very elliptical common envelope onset ever survive? Is that something that makes them just merge? Okay, so eventually you get into the end spiral, the dynamical end spiral. And if a merger results, for example, you could have a very, very low mass companion, just goes into a merger. The star doesn't feel very much. It burps out a bit of energy, and that's that. But, and we've often thought of that end spiral as kind of the happy part, the part that we understand best is really fast, that simulations can really deal with it. But again, Paul, thank you. Paul Ricker sent a question is, what diversity, what might we expect in that end spiral? And what happens in the massive stars regime, which is the part that we know the least because there's been the fewest simulations, and they're really messy, massive stars. So what happens when you get those stars? What does end spiral look like? Eventually, you have a post-end spiral. What does that mean? It means that the orbit stabilizes. Now, it stabilizes. So there's the lengthening of the time scales, the orbit stabilizes, but it may not stabilize for long. It depends, right? So now you got the stable orbit, you look out to see the envelope, and what do you see? You might see an envelope that's mostly unbound. Fine, great, it's going to go away. But what if there's a little bit that's still bound and it's going to come back? What if it's 10%? Does it form a disk and doesn't disturb the binary anymore, or does it fall right on the binary? And if it does form a disk, what does a disk do to the binary? Now, on the other hand, if you look out and you look at your envelope and most of that is bound, it's going to come and fall back, maybe eventually lead to a merger. So this is going to be some kind of a cupping common envelope. Maybe there's some in spiral that ejects the envelope again, but then the envelope comes back once more. We just don't know that part. So there's clearly a longer time scale, messy thing that happens after the common envelope in the case that there is no just an obvious merger right away or an obvious outbursting ejection, if those even happen. Okay, so again, in the first topic that is we all care about is that wretched final separation. If only we knew the final separation for every single type of binary that goes through a common envelope. These are 2 random plots. We all plot these plots in simulations with kind of the end spiral and the stabilization. This stabilization has a final separation. Obviously, it's not one value. The thing is here going down a little bit. Here is a lot flatter. We can argue to our heart's content what is the final separation, but we know that those simulations give you something. And if any of those things I said before happen, that final separation may change. So clearly it's not final. Now, with observations, on the other hand, particularly that some types of observations, which are the simplest post-common envelope, these are like a single degenerate white dwarf plus main sequence. They've gone through one common envelope. There's not been any crazy supernova stuff going on. So this is pretty simple. We look at the separations, and those are clearly the final separation for this stage of evolution. Eventually, things might go into the nova regime and things change again. But ultimately, these are the final separations. So the question is, are separations derived from simulations and observations the same? Likely not, but how do we connect them? And here in this colorful plot, we have in black the observations and in colorful is the simulations. And they actually even look like they half agree with one another. It turns out that this comparison is multidimensional. This is just one of the planes that looks the best, but actually it's a lot messier. But the point is, can we compare these two things? And the answer is, maybe not quite, maybe not for all simulations. It depends on a lot of parameters, whether the envelope was unbound and other things like that. Okay, so next question is envelope ejection, and I'll sit on this for a few slides. So what is the envelope? Okay, there's a core and an envelope. Well, that sounds like a plain Lego, like you have a brick is the core and 10 bricks is the envelope. It is really messy to make that determination. For my beloved post AGB stars, you have such nice little dense core, and then you have the envelope. And even for those, it's hard to determine what the boundary is. And there's a lot of binding energy in those layers of envelope just close to the core. Here on the right, we have a picture from one of the papers that has explored this, in this case, for a very massive star, where we know the binding energy of the star, and we all know the delivered orbital energy by a bunch of different companions. Now, depending on where this thin line is positioned, you might or might not survive that common envelope, depending on where you decide the envelope finishes and the core starts. And again, Paul asked this really good question this morning, saying, well, what if the core is burning? And you have, or partly burning. I mean, suddenly you get a very complex stellar structure, and determining what the star will do upon the ripping off of part of the envelope is messy. Now, this is not so much a question now, but it's one of those things. And actually, Justin just sent me an email minutes ago saying, well, make sure that you're clear about this, because it's confusing to people. And we often say something and mean something else. So what does unbound mean? Well, we say, well, the envelope is unbound when its energy is positive. But what is the energy? Okay, well, so you can say mechanical energy, kinetic plus potential. That's great. That's a nice strict definition. That's basically meaning stuff is flying off at greater than escape speed. But then you can actually decide, well, if the envelope's very hot, that thermal energy is going, effectively could unbind the envelope, even if right now that bit of gas is not flying off at the correct speed. And then you can say, well, what if instead of thermal, I use internal energy, which here it includes not just the thermal, but also the recombination energy. Now, on the bottom two panels here, you see how changing what you call bound and unbound may give you more or less unbound mass. So here, I'm even going to say there is no right or wrong, but please, it's very important to be really clear what the word means, okay? Internal energy in an ideal gas simulation is thermal energy. Right? And so we just have to be clear with the terminology. Now, we talked a little bit before, what if you're unbinding most of the envelope, but there's a 10% or a 5% or a 1% that comes back and gives you material that may fall onto the binary, or given that it's trying to spin up, is going to form a disk. What does that disk do? And here there's a work from Amit and Noam a while ago saying, well, a disk could change your binary parameters inside the disk. And here, there's obviously these timescales are very long, but it is still the question is, what are our final separations? So if it's changed by a disk, we need to take that into account. And on the right here was a feeble attempt at looking at our post-in-spiral gas after the orbit is stabilized, and looking at to see whether anything is coming back. Unfortunately, I think the simulations don't go long enough to follow that. And of course, there is a recombination energy. So we all know that envelope expands. Here, there's a lovely picture from one of Natasha's papers where you see the expansion and the hydrogen recombines. Of course, also helium recombines 3 to 2 and 2 to 1. And you have all these recombination fronts with energy delivery. And the question is, if you use that energy and you translate it into, you thermalize it, so it becomes thermal energy, it can unbind the envelope. But if you were to radiate it away, then you're going to depressurize that way of unbinding the envelope, and you'll maybe unbind it less. And you all know there's been a series of papers, some by Noam's group and some by Natasha's group, arguing about just how much can you eliminate that energy and how much you retain to do work. So that remains a big question. Now, convection has been bothering me for a very long time. In fact, I remember a day when Ron Tam visited me in New York, and we were talking about that. And he said, look, everything is so fast, you know, that you might not have to worry about pretty much anything except the dynamical. There's a very nice paper, in fact, there's two papers by Emily Wilson and Jason Nordhaus, taking a look at delivering orbital energy to your common envelope, and then making a decision if that energy is delivered in a convective area that is in touch with the surface, and if the time scale of that convective overturn is fast enough, then that creates an inefficiency. So suddenly your alpha basically deteriorates. And here we have a whole bunch of primary masses up here and some down here, where you are really looking at a very low alpha in the sense that your orbital energy is wasted. It's convected out of the star. In that case, you might have a hard time to eject the envelope. Now, topic number 4, alpha. I mean, I am so tired of alpha because it's tricky, okay? So the alpha formalism is deceivingly simple, and I got a nice little equation here, and it's simple in that form because we are hiding into the details of the binding energy you're going to calculate and the orbital energy you're going to deliver, or whatever other energy you might include there, a lot of details. Now, the reason we insist on this alpha is because it can be handy to have it as a parametrization by which you quickly figure out the final separation of a system. And of course, population synthesis have used it for a very long time to create all manners of populations where binary populations where a common envelope is involved. Now, I guess the only thing I really want to say is that every person, every group that tries to either determine or use alpha does so in a specific way. So on the left here, we have a beautiful reconstruction of post-common envelope binaries, where one way or another, you know the binding energy of the original primary, and you know the final separation, so you know everything except alpha, so you can calculate alpha. Now, this is tricky at best, even if this is probably one of the best ways we have. You can see how the error bars are really big. So fine, there's just some alpha in that way. The simulations can use a similar method and be even compared with the observations. Of course, there's that caveat of what is the final separation in the simulation. And then, of course, there's the alpha that was calculated in the paper I mentioned before, where you say, well, all I'm saying here is that we're going to take orbital energy bit by bit, and its delivery is going to be nullified if it's in a convective area that transports it out quickly to the surface. So the important thing is, no matter what alpha a paper gets, it's very important anybody who uses that looks very carefully to reconstruct the formalism that paper used. And of course, even if you're clear about that formalism, there's just so much complexity and so many things are not maybe stated properly. I just think it's a real Pandora's box, this alpha, and I don't really know what to do about it. So there's no question in there, you may notice. So the question is question mark. Okay, so now we're on observations. So observations, I'm talking about two things. First of all, post-common envelope systems that can give you useful parameters. I was talking to Ilya Mandel just the other day, and he said, oh, what about double neutron stars? And I'm thinking, wait a minute. Those things are messy. They've had 2 supernovae, 1 or 2 common envelopes. It's messy. But this guy's here, this lovely picture. Actually, I saw Howard here, and he will know what this picture is. And in fact, I believe I might even have pilfered it by one of his talks a long time ago. And he's actually an artist's rendition of a central star or planetary nebula illuminating its post-common envelope binary companion, which is in this case a main sequence star. So these stars are really great because they're as simple as they get. I mean, you never use the word simple, but anyway, you see what I mean. So we have a lot of them, and there's a lot in the Sloan Digital Sky Survey. This is just a piece of a table that actually reproduced one of my papers, but was actually from the Zorotovich paper. And so with lots and lots of data on final separations And up to a point, also the masses of the components, obviously with caveats. If you have an eclipse in binary, obviously that's a lot better. But here we can do so much more. There's this paper that came out very recently, but it's not the only one. There's one, I can't remember, Dave Jones would know what started is, where the companion, the orangey thing here, has been polluted because it has accreted material from the AGB or the evolved star. And so we see that in the carbon bands in the main sequence star. And when you do that, you can just about calculate how much mass you've accreted. And so this paper concludes that this mass is too much for the common envelope to have given it to the star, and probably was before through Roche-Loeb overflow. The question is, maybe there is an avenue to find how much accretion happens in a common envelope. Probably it's very parameter dependent. Probably we can only do for the low mass. It'd be very interesting to know what happens to, say, a neutron star going through a common envelope. Talking again of post-common envelope systems, here are a system that I call Van Winkel objects. Hans hates it when I do that, but these are amazing. They are binaries, but they have periods between 100 days and about 2,000 days or so. Well, the ones of 100 days would have had a really hard time avoiding the common envelope. However, they're clearly not normal common envelope objects because otherwise their separation might be a lot smaller. So what happened here? Now, all these binaries have disks, and this is one of the most pictures ever. It's a reconstructed picture from the VLTI showing the circumbinary disk of one of those objects. How is the disk related to the weirdness of these objects, their orbital parameters? How much mass, do circumbinary disks exist all the time, or is this a special class? And does this famous grazing envelope evolution that Noam wrote about exist? Does it happen? Do you have failed common envelope where you just get a little bit of common envelope and then, hey, you give up? These objects are certainly holding a lot of keys. And what is also amazing about these objects is there's an awful lot of measurements of them. Why can't I change my slide? Okay. So, another thing about post-common envelope systems is that many of these post-common envelope binaries are in the middle of planetary nebulae. In fact, at least 1 in 5, and that's a strict lower limit, of central stars are in such systems, and the nebula around them have all manners of morphologies. In fact, many are jets, but not all, and some are more or less elliptical, and some have very bipolar shapes. And the question is whether these are blueprints of the common envelope. And there's initial work that started mostly by Guillermo, and partly by the Rochester group, based on different common envelope modes. Modes means you get a common envelope and then you freeze it, and then you take that output and then put the planetary nebula through that, and then you study what happens. Now, this is the early days for the simulations. There's still a lot of things that need to happen, but it's certainly a start. And the question is this a really great way to learn about the common envelope within by whatever has been ejected? So enough with post-common envelope binaries, and let's talk a little bit about transients. Now, transients are kind of they're not a new thing. There's been transients for a long time, but now we're seeing so much more thanks to all the great surveys that are out there. So possibly most observed transients are massive, and that's just because we're probing a bigger volume, and obviously we need the brighter object, and there is a correlation between brightness and mass. Okay, when observed well, the numbers that you see in this slide from a paper of Morgan McLeod are really good, particularly for theorists. What I really love is the growth of the photospheric radius. And that's because we can actually look to compare that with simulations. If you give me the luminosity, the bolometric luminosity or the luminosity through filters, that means that the simulation have to make a light curve, which is still not quite there. So this is a fantastic output from transients. Ejector velocity, if measured close to the outbursts, are also really easy to compare with simulations and a very good one to do. David Jones reminded me of this, which is really true. So there's a whole bunch of pre-planetary nebula out there. They're not planetary nebula because the central stars are too cool to ionize, or kind of they're about there, but they're too cool to ionize. So these are different objects. We've always assumed that they become planetary nebula eventually. However, the shapes of these guys are really, really elongated. And here's two extreme examples. The question, and they're very young, they're kinematically hundreds of years old. So are these transients from the recent past? We didn't see the transient, but we're seeing the aftermath. And once again, what are they telling us about a possible common envelope? I will tell you a lot more, and I won't tell you a lot more about this because it's going to be a lot more in the planetary nebula session, but there's a lot known about the stars and a lot of mysteries as well. Now, of all the transients we've seen so far that we call post-common envelope transients, there's probably, I don't know, maybe 10, 15, 20, 15, I don't know exactly. But here is a nice slide from an oldish paper by Nathan showing a bunch of light curves. And the interesting thing is that when you read those papers, you say, but was that a common envelope merger or was it a surviving binary? And you never quite know. That assumption is always a merger. And I found in one of the papers, I can't remember which one, but it says it's likely these are all mergers. But in some cases, if there was a surviving binary, you might not know for a while. But if these are all mergers, why are we not seeing the surviving binaries? Maybe they're dimmer. After all, the merger goes all the way, more mining of energy. But we would love to see some surviving transients because that would give us, a proper counterpart. We're excited about the transients because they give us some observational confirmation. But if we don't see the surviving binaries, then we're perhaps looking at a different kind of objects, the one that merge. Okay, so here is my last part, and it's on theoretical considerations. And I have divided it by type of simulation or type of theoretical approach. So talking about global 3D simulations, such as the ones that give you the whole binary and the companion and the whole inspirer and the ejected all in 3D, there's a bunch of things that must be added if we are to make any progress, and some that maybe should be added, but maybe not yet. And actually, thankfully, Fritz Röpke, who I think is here, was writing this review mostly on computational things. And I'm giving him a hand, and it was a very nice way to list a bunch of things that we might need. So radiation transfer is probably very important at this point, because as we go into massive common envelopes, we kind of really need it. First of all, it would resolve the issue of recombination energy release. Also, it might it's important if we go into slightly longer time scales that with simulations like this, you can't go into very long time scales, but you can probably stretch it a little bit. But at some point, you need to radiate. Magnetic fields have been explored by Sebastian Ullmann. Certainly a lot more to be done in that arena. Whether it's needed right now, we might be able to park it for a little bit while we fix other problems. Convection. So in Sebastian's first paper, there was this picture in the middle that talked about whether they were seeing convection. Now, the envelope it's got a flat entropy profile. So this is a convective star, but there is no energy source in the middle, and it's not radiating at the top. So whatever it is, if we're to simulate it, this is not going to cut it. And of course, the other issue is that resolution is never great in this simulation. So, but what to make of that? So maybe this is one of the things I would love to hear opinions in this conference about what is convection, lack of convection in simulation stopping realistic results. Accretion onto the companion, is it important for the actual dynamic of the envelope? What if you have a neutron star? And how are we going to even model that when things are really difficult with neutron stars, both about accretion and feedback and with shape and how you're going to do it? But of course, there has been some work done. Luc Chamandi has done some work a couple of years ago on Aloma stars, really looking at subgrid models of that companion as it accretes. And of course, the question of dust. Well, dust forms in these things. We know that from observations, and we know dust can form very rapidly in dense environments. So, and that, if it does form, then it's going to potentially drive mass loss. So that might also be important. Okay, another really big issue with 3D globals is that we have the companion and the core often modeled as point masses with a softened potential. There's very little investigation of just what that does, and what if you change the softening radius? What if, what is it doing to the companion? Actually, there's some wind tunnel models I'm going to talk about in the next slide, where you can look in detail about accretion patterns around and what different accretion radii do. But this is, I've just put this 3 little bits of text from 3 different papers. Pretty much everybody does the point mass. In the paper of Paul and Ron Tam, there was actually a slightly different approach. And again, but there's no investigation. If you change that to something else, what happens? So finally, for 3D globals, this is not a question, it's just a reminder that we're never going to be simulating the whole shebang. We do the dynamical phase, we can do a bit before and a bit after, but in the end, there are limits to what explicit time-stepping codes with the current condition can do. And so that leads us to 1D structure simulations, particularly when they have nice little modules with hydro. So this is a really recent paper by Tassos Fragos that did the whole common envelope. Oh God, this I think was a 12 solar mass star with a maybe 1.4 solar mass companion, and they did the whole thing. The position of the energy during the in-spiral is done by some parametric formalism. So say I'm going to deposit it here now, and then here, and how much, and then it's put in as heat. Now, I would have liked to make this slide a bit more interesting. There's a paper by Natasha, so it's in Ivanovan, and that's 2016, and she talks about issues with doing that, and she suggests that perhaps depositing energy as kinetic energy, so as motion of the particles instead of heat, might have better outcomes. But the point is, should we model in spiral in 1D in the first place when we have 3D? Wouldn't it be better? Okay, I don't know if here people are going, no. Wouldn't it be better to just do the in spiral in 3D and somehow interface that with 1D with in some manner, you're going to have to spherically average things and give just one profile, put it in the 1D and then know what to do with that. But there's some work already starting in that domain. And of course, this is from Natasha, but there's some really nice work done by the LSU group on these are not common envelope, they're post wide dwarf mergers mapped into MESA to see what the long-term evolution nucleosynthesis is. So there's lots of stuff happening in this regime. And I think this is going to be a very nice type of tool. What about known global 3D? So for example, wind tunnels. So you are not looking at the whole thing, but you're looking at a box in 3D and you put the companion, and here there's a little picture from the first of 3 papers on wind tunnels that Morgan McLeod is involved with. And then what you do, you say, well, we got analytical ways to tell us the gravitational friction that can be used in all kinds of parametric models. But by doing the wind tunnels, we're going to correct those analytical prescriptions and make them better. So here there's a nice little comparison between the analytical prescription adaptation versus the analytical prescription raw, and showing that it's a little bit different. And really nice paper by Luke Chamandi, where they did a global simulation, but they compare the gravitational friction force that they get, which is the black line, versus the one they can predict using the prescription from the wind tunnel. And as you can see, there's a difference here. And the question is, what do you do about that difference? Obviously, we're not believing anybody, right? We're not in the game of believing, but it's a question of why this difference and how do we reconcile it? Finally, there is, of course, the population synthesis code. We often think of population synthesis as customers, right? They want to get the alpha or other things so they can carry on their beautiful predictions on all manners of populations. But they can also be used potentially, I think they can, to constrain parameters of the common envelope, such as final separations or alpha, if you will. And for example, here there's a very simple plot where 3 different alpha prescriptions give you 3 different period distributions, as you might imagine. And here on the right, a paper by Sylvia and Heiss showing that with different alpha prescriptions, you eliminate the predicted long period tail, which is not seen in observations. So these are other tools which, well, they are being used. The question is, though, how do we reconcile and connect those findings with the other side of things that are also talking? This goes back to the alpha thing, and you can see, this is alpha lambda, this is slightly different. So how are we going to reconcile these numbers? And this is my last slide, and it's going to crash my PowerPoint presentation in about 30 seconds. So what about toy models? So toy models can be very powerful because they allow you to do things that you'd never do if you were to do a proper model. So here, Sagiv put some jets inside the common envelope. And this is a regular common envelope ENSO simulation from, it's the same as the FAST 2012. And we find more unbinding, fantastic. But there's a lot of buts and a lot of ifs. Does the disk even exist? Do you get jets in this particular situation? So toy models can be a little misleading because if you do something like this and you're wrong because it was a toy model after all, then might it hinder further progress because people say, oh, it's been done? Or might it inspire further progress because this is clearly not right, but we can do better probably. So what is the role of toy models? And so I have finished. This is basically the list from the previous slides, and I've put that on Slack. And I would like now to stop here and leave the floor to exactly 30 minutes, leave the floor to the session chairs. And not every session chair is here right now, but maybe to add a few things or a few comments, and then that's it for the beginning. Don?
Ursula, you lead the discussion, please.
Oh, I lead. So I was inviting you. You had a couple of slides of questions, which were quite keyed on jets. Paul was talking a bit about more massive stars, and this is kind of a really new thing as there are more simulations coming up. So feel free to budge in.
Yes, so do you see my screen?
Yep.
Okay, so I have some questions and answers, but
You're giving the punchline, no answers.
Okay, the punchline can in some cases we get alpha parameter, what we call alpha parameter, but it's not a universal parameter. I think it is different in different systems. Can it sometimes be more than one? And I think, yes, if we can launch jets, in particular, if we have neutron star or black holes as companions that accrete at a high rate, and many, I mean, 4 or 5 different studies require alpha common envelope of 2, 3, and even more to explain neutron star black hole binaries. Second question is, what is the accretion rate inside the common envelope relative to the Bondi-Hoyle-Littleton one? Like the results of the McLeod group that you showed give less than 0.1. I think it's between 0.1 and 0.5. Later in the meeting, Shlomi, Leila, and Dana will comment on that. A combination energy, I think it has some role, but not a large role. Note that the recombination energy corresponds to a velocity. If you take all the recombination energy in a solar composition and give it to kinetic energy, it's about 54 kilometers per second. So it does not help you with massive star and compact. So even if it works only in very low mass, and not very, but low mass and large giants, and do a part job. And again, convection can transport the energy out. Does Circumbinary form? Well, you raised it. I think in many cases, yes. Angular momentum is large, and we cannot eject all envelope. We know that. So, and we do see in those post AGB stars, post AGB binaries that did not enter the common envelope, we have the resolution, and this system live for a long time, so we can see the disk, and we do see them. What is the outcome of companion core merger? If we go back to your picture that you show the final orbital separation, it doesn't drop to the minimum. It's like a wall. It means if you go to lower separation, the companion actually and the core sometime merged. So I think in many cases we will have merger of the core, and the companion can give you type 1a, very bright transients. If a neutron star or black hole enter the core, and these are things that my group studied. I know I'm going to the extreme common envelope cases, but maybe this will teach us on the more common cases. And this is, I stop here because there are other people.
Thank you, Noam. Maybe Paul, do you want to say a couple of things?
Sure. So I don't have any slides. I'll have a slide or two tomorrow. But and you captured my questions to pretty accurately, I think. A couple things that I think would be, I think there's more work that needs to be done with simulations. You mentioned the transitioning 3D global simulations to 1D simulations to follow long-term evolution. And I think it would be good to identify criteria for, how far does the 3D global simulation have to go before we trust the that procedure. You mentioned expansion of the photosphere and predicting light curves. I think there's still a lot of uncertainty about how we handle, like in simulations that involve a fluff, how do you handle the radiation in the fluff region? How do you identify the photosphere, especially if you can't resolve the atmosphere of the star? And then a final one, I think a lot of work needs to be done on is actually paying attention to the GR-MHD accretion community, and specifically simulations of super Eddington accretion. So if we have jet power helping with envelope ejection, that's going to be in a regime of accretion that's not the one that's typically studied, to understand systems like M87. And there's relatively less work on it. And I think doing some more simulations in that area and taking the insights from that to inform our subgrid treatments of accretion is necessary. And so I'll stop there.
Thank you. Does anybody else want to say something specific? Or Stephen, do you want to say something about, you were one of those who mailed me and had some questions?
Thanks. I think me adding any more now would probably not increase the amount of information people retain at the end of the session. So,
well, then anybody can chip in. Fritz, hand up. Frozen. Oh, here it is. I'm not sure if I'm frozen. Do I see other people moving? Fritz, you're muted.
Yeah, you're frozen for me, at least for a moment. Right. Okay. Yeah, I just wanted to add a couple of thoughts about the simulations that we do. And actually, you had the slide of what is needed as an input. And of course, there's these things that we have to add in the future, things like radiation transfer and maybe magnetic fields. And I will talk about magnetic fields. And I think they are not so boring after all. So I will actually sort of say some words about this tomorrow in the beginning of my session. And also things like dust. And so that's additional physics. But even if we actually just consider the very basic model, which I like to call the Gravo hydrodynamic model, where we actually only solve the Euler equations plus gravity. And that, of course, gives us already the basic common envelope model. Do we understand that in 3D simulations? And so one thing that I think is still not completely settled, but needs to be settled, is why do we actually see sort of the end of the plunge-in phase? And what actually sets the final slope there? Why is it actually that the in-spiral in the end gets shallower and slower? So what is that actually that reduces the drag force? And there are many effects in this regime. So this is actually sort of the drag force depends on the Mach number. The Mach number is low, then is it co-rotation? Is it because the envelope is partially lifted? Which of these effects is actually dominating here? Is there a dominating effect, or all these different effects conspiring to actually end the plunge-in phase? So this, I think, is not completely settled yet. And a question to the very basic model, the simplest model that we can think of, even just with an ideal gas equation of state, not taking recombination energy into account. The other question that you actually sort of raised there is the numerical issues with that problem. And I think the gravitational softening is actually one problem. Another problem is also the way we set up the initial primary star. And what we do, and other groups do too, is that we cut out the core. And the question is, does it matter where we cut the core? And how do we replace the stuff that we actually cut out? Is that all put into the point particle? Do we fill the innermost cells with gas? And if we do so, what does it actually mean for the final orbital separation that we get in these simulations? What does it mean if the final orbital separations are smaller than our cutout radius? Is that a problem or not? So I think these are still open questions that really are sort of posed by the very basic model, but still not answered completely in 3D simulations. And then sort of the termination of the plunge-in phase and the in-spiral that we see in the 3D simulations, is that something that carries over to 1D simulations that are inspired, for instance, by wind tunnel experiments, because here you actually sort of dump the energy, and if you have an envelope response, then you actually sort of dump the energy in a spherical shell, not really into something that is more complicated. I mean, we don't really have a spherical geometry anymore in the 3D simulations. So I think there's lots of open questions with respect to 3D basic simulations coming in.
Okay. Anybody else wants to make a comment?
Fritz, what is your view about the recombination energy? You are now filling to the common envelope evolution. How do your group treat the recombination energy?
Well, what we do is actually what many others do. We actually just use the Opal equation of state and then assume local thermalization. And of course, that's the upper limit, right? So that's actually when you assume that all the energy can be used for envelope unbinding. And so we've just with Christian Sand looked into where the recombination energy is released, whether this is at high optical depth. In most parts, it seems to be like that, but that's our current treatment. Yeah. And then we do the simulations without common envelope, without a recombination energy. That's the lower limit, right? So you have an upper limit, a lower limit. Yeah.
Can I say something that I don't have the answer to, but I remember again, the Natasha paper that I quoted a lot, there was this issue that recombination energy, let's say that, fine, we can use the whole payload. It unbinds the envelope effectively up to, I think it was 2 solar masses. Now there'll be some talks about massive common envelopes, I think, in this conference, showing that actually unbinding can be effective in more massive stars. So it's not just whether the recombination energy should be retained or radiated away, but even retaining the whole thing, there's going to be diversity on the property of that recombination energy for the envelope unbinding, depending on what the type of star that this is happening to is. Do you have preconceived ideas on what it's going to do to massive stars?
I think to massive star recombination is not important because, again, recombination in solar composition translates all recombination energy to a velocity of 50 kilometers per second. So for massive star, it's not so important. For low mass star, the envelope can unbind itself. You know, if you take all recombination energy of an AGB star and it recombines, you just do the energy, it can unbind itself. It doesn't happen, of course, but in principle, it doesn't happen.
Any more comments? Hands up. Paul?
Yeah, I just wanted to comment on Noam's comment there that, yes, formally, you know, the massive stars would have a lower or smaller reservoir of available recombination to use, right? But it really depends on how far in the in-spiral proceeds. That Krokov paper that Ursula showed a plot from also, you know, looked at this as a function of donor mass, and just sort of hypothesized what if, you know, you moved the core of the massive stars into one solar mass, and it was significantly more greater amount of recombination energy that you could tap. So, you know, I agree that there's going to be diversity, but the answer really depends partly on this question of where does the in-spiral stop and what determines that.
Thank you. Morgan?
Well, I guess I just wanted to highlight something that I was hearing both in your initial slides, Ursula, and then in Fritz's and Paul and Noam's comments, which is that, you know, this is such a big problem that maybe there's value in dividing it into these portions temporally which kind of run together and are messy and that sort of thing. And whatever we can do to understand one of those chunks, and by understand, maybe I mean understand it well enough that we can put it into a toy model and capture some element of the representative physics that can then be exported to the sorts of parameterized solutions Ursula was highlighting, then that's a really beautiful result, because that's one less thing that we have to sort of simulate all at once. Maybe that's something we can all think on as we sort of listen to all of these talks, because there's something beautiful there about breaking down this sort of big intractable problem into more tractable little chunks. And each one of those sort of minor victories will probably add up, hopefully over the course of time.
Thank you. Hey, Adam.
Hey, just a couple of comments. First, your point that you made about the different definitions of binding energy, I think is really important, and it's maybe something we can try and sort of systematize at this, because you see lots of different definitions, and it strikes me that those different, in our own work, those different definitions have, they can lead to confusion unless you're really clear about what that means. And we might have, I was thinking community-wide, if people are going to use different ones, we should have names for the different ones rather than asking each, the reader to always go back and kind of figure out what the what was meant, what that particular paper used. So that was one comment, and then the other comment is about the wind tunnel. These kind of subgrid models. I mean, there's so much the importance of subgrid models. I'm struck in these, in these kinds of simulations, the importance of them. And, the wind tunnels sort of allow you to do to unsubgrid the subgrid model at the expense of not having a global simulation. But there's some work to be done. It's not clear to me how well they do after the first inspiral or the first plunge in, because by then, there's so much disruption of the environment after you've done one orbit that have we successfully, do we know how to treat that kind of situation with all the turbulence or whatever is happening once with a wind tunnel kind of simulation. So those are just my two comments to start off with.
And what if the wind tunnel was interventionist, Morgan? What if you took your global up to a point and stopped and did a wind tunnel there? So it's insertion. You just put it in.
Yeah, and maybe this goes along with what Adam was saying in a way, because one question would be like, what are the conditions that would inform the material that was coming in? And then another question is like, how separable is the interaction on that smaller scale from the global scale? And I think that we don't know either answer to 100% clarity, but if we were to find that there was some separability, I guess the result would be that, if we knew the properties of the incoming material, then we could sort of zoom in and simulate that interaction and get some result that was then applicable to the larger scale. And so maybe a question we could ask is, when the sort of global simulation and the wind tunnel simulation start to deviate, does that have to do with different incoming properties, or does that have to do with some tighter coupling between the orbital evolution and the small scale properties? And I don't know the answer.
Okay. Fritz, do you have another question, or is your hand still up?
No, there was another question, and but that's a bit of a different topic. And the question here is, so the initial sort of big questions in common envelope simulations was, what is the final operator separation, and does the envelope get ejected? And the original idea was that this is related, right? And now in the simulations, it seems that if you actually include recombination energy, you're able to eject the envelope. So one problem is solved, but the other problem is not really solved, because I think most of the simulations tend to find final operator separations, at least during the time that we are able to simulate in 3D, that are too large compared to post-common envelope binaries. So what is the view on this? Is that really a problem, or I mean, do we miss some physics that sets the final orbital separation? That would be perhaps then kind of effects that take place on long time scales, like circumbinary disk or something like that. What's the ideas about that?
Well, if we only got the answer to that in this conference, I'd be very happy.
But in a sense, also to mirror that, that's like, this is a great time to ask that question because we can think about it as the talks go on.
Yeah. Anybody else from the younger audience? Don't be shy. We used to be young too. Hard to believe, particularly for Noam. Well, again, no.
Whenever there's young people, I jump in. It's a habit from 30 years ago. When we talk about what happened at the end, the final orbital separation, I think we should look at the young stellar community or the people who do planets. In the past, it was thought that planets form and stay there. And now migration is a big issue with planets and all bodies around stars. And I think we might call it even migration. Maybe our final orbital separation is not final by the time we eject the envelope by the definition of most of the envelope. And we do have some circumbinary or other material falls back, and we have some migration. I don't know. I didn't solve the problem. I don't know. I think in many cases that circumbinary material and the final orbital separation and the final envelope mass are not well defined. And again, it goes to what Morgan suggested, break the problem to small problems. So when maybe one of these small problems is let's leave it at final orbital separation larger than what we would like to, comparing to observation, and leave a little bit envelope mass with angular momentum and see what is going on.
Yes, we might actually, Morgan just said in the chat, we might adopt migration. Let's steal it. Planet people have so many things. Alexi, there was a question, but did you? No.
I had a question, a comment. So the comment basically is that, well, in binary populations, we probably mostly care not about exactly alpha, but exactly about the final locations or the final orbits of the binaries. So, right. So if, for example, Monika Zorotovich compares the Wide-Dwarf sequence binaries, they do care about getting the final orbits, not exactly the alphas, which leads to those orbits. So perhaps maybe one thing which we should care about is really like checking that this overall functional dependency of the final orbits on the initial parameters given by the alpha lambda formula is still correct. So in other words, there's this alpha GMM over R and so on, so that this dependency still holds even if you try to have a realistic picture. So that was a comment. And a question was about the common envelopes is basically that about the final orbits of the 3D simulations is that if we start the 3D simulations, then sometimes the binary, the donor star, when the common envelope phase starts, is not necessarily the same period when the donor star is when the mass transfer starts. So in other words, mass transfer starts, the mass transfer rate goes up, and the period changes. And also common envelope can onset quite quickly. So in other words, the point is that the donor star is not necessarily in synchronism with the accretor when the common envelope phase starts. And the rotation in a synchronous star contains kinetic energy, which might be potentially important for the final energy budget. And the co-rotation, I believe, is always assumed in all the 3D simulations. So that's kind of a comment and a question. So, perhaps maybe a thing to perhaps reflect. So does the rotation energy budget for co-rotating stars potentially have influence on the final orbital separation?
That's a good point. And actually, I would, you go back to the Sandquist papers and they do test that. They do rotating versus non-rotating. But we have to be wary when somebody says, well, we tested this and it doesn't make any difference, or it does make a difference, that's not the final answer. First of all, because they were older simulations, but also there were specific parameters. So I think that's a general point for everybody. Just don't be shy, try again, because the answer might change. And and actually the rotating or no rotating state of the primary depends. Some simulations will go in the co-rotating frame and allow synchronized stars, and others don't. So it's a really big mixed bag. So point taken. Was there another? Before I feel I missed something. Steve.
Hi. Just a couple of questions that I hope might be useful for discussions. Regarding the rotation, for example, I think there's an issue of whether you treat it as cellular or genuinely differential, and whether there might be circulations set up during the course of a merger or during the common envelope, because the way that the accretion is going to occur could very easily lead to, say, equatorial spin-up, but this is going to then transfer angular momentum into the interior depending on things like the convection patterns. Okay, that's just a side comment. The other is something more for Noam. This question about Bondi-Hoyle that I've always wondered about. The assumption in Bondi-Hoyle-Littleton is that gamma is constant, but if you have the accretion and it's forming shocks, like in a wind tunnel, what does this do to the upstream structure? And how does this affect the flows when the accretion is finally occurring in the last stages before merger? Those are just two things that come to mind. The third is, you were talking all about kinetic energy versus potential energy, but you got to remember there's also the turbulence stress. And so if you're generating turbulence, this can be a sink for the kinetic energy that is going to restructure the envelope. It's not convection. That's not what I'm talking about. I mean genuinely induced turbulence, like wake structures around the merging stars within the common envelope. You know this from actual wind tunnels, where you're accreting material and it goes through ionization, and then in the wake you have strong turbulence. This can be strongly dissipative. And so it might, in fact, counteract the recombination if you have sufficient energy release from that. So one of the things that might be necessary to include in the simulations is a turbulent viscosity that's calculated self-consistently within the context of the envelope and merger. I don't know if this has been done. Pardon my ignorance here.
Is there a way to calculate, to do a first back of the envelope, knowing the conditions in the envelope, to know whether this is going to be prone to a significant turbulence?
I think sort of, kind of. At least you have sufficient stuff from decades ago for what happens in these flows. The problem is you got this squishy thing that's merging or that's moving within a common envelope, and that creates problems because it's entirely compressible after the shock. It's a low Mach number. So you've got slip instabilities. In other words, you've got Kelvin-Helmholtz at the boundary, and this can also generate thermal instabilities, but I think there are ways of doing it. At least, if somebody wants to take 10 years for a doctorate. So those are just
thank you.
My comments.
Any more comments? We're actually at the end of the hour. Can I ask you to whether you have some additional comments or something might come to mind during your break? Or in general, I've tried to capture some of these answers and questions with attribution in the Slack channel. But it'd be helpful if you just type in yourself things that you thought. I think we can call it a close of the session. We're going to have a 10-minute break right now. And then we're going to start with the next session, which is...
we have 10 minutes break and we resume after that. Okay.
Yeah, and then we have a Post AGB that avoid common envelope.
Thank you, Ursula.
Okay, thank you, Noam. So welcome back. We start the science sessions with the session entitled Post AGBs that avoid common envelope evolution. Now, Ursula asked that the session chairs have a little bit of an introduction when we set up the sessions, and really, I don't think this session needs much of an introduction other than to merely say that there's the sort of overarching question that I think relates entirely to this session, and why would we discuss non-common envelope objects in a common envelope conference, is exactly what is it that defines whether a given system will enter a common envelope or not? Why do some relatively close binaries manage to avoid the common envelope, and why do some plunge in? And this is very strongly related to the next two sessions with Post AGBs and planetary nebulae, in that there is a significant population of Post AGB binaries that Ursula referred to in her introduction. She called them Van Winkle objects, but I would call them Van Winkle and Kamath objects because of the more recent discoveries of the Post RGB equivalents of Hans van Winkle's Post AGB intermediate period binaries. And these are systems that lie in this kind of parameter space where you might expect there to have been a common envelope, but somehow, probably through stable, non-conservative mass transfer, managed to avoid the common envelope. Now, unfortunately, Hans was scheduled to speak in this session, but couldn't make it due to a thesis defense. So his talk, which would have been the general overview on these post-AGB binaries, is postponed until Friday. But nonetheless, I think we have some really interesting talks in this session that should hopefully shed some light on this subject. So let's start with Bruce. And so officially, we have 12 minutes for the talk and then 4 minutes for questions. I think we have enough flexibility that I don't have to be too cruel with the timer, but nonetheless, Bruce, I'll give you a 2-minute warning when you have 2 minutes left. Okay?
Thank you very much. And I got to say, after 50 years in this field, it is amazing how much progress has been done. When I think of the work in my thesis and about that time in planetary nebulae, the first IAU meeting that I attended, the things we will talk about today weren't even dreams. It's amazing how far we've come. And we've been propelled by instruments and numerical simulations made possible by high-speed computers. The revolution is spreading all around us, and I hope we all take notice of that. Okay, I want to try to get my talk onto the screen. I don't know what you're seeing. Are you seeing anything other than me?
No, we still see you.
I don't, then I'm in trouble. Do I have screen control? Share screen.
You have the, yes, share screen.
No,
share screen and
I got it.
Yeah.
Now you see something?
Yeah, now we see your PowerPoint. I think you need to go full screen with it, but then we should be able to see everything.
Okay.
There we go. Perfect.
Wonderful. All right, now this is a talk which was scheduled to be at the end of the meeting, and I thought that was a very prescient choice on the part of the organizers, and you'll see why in my last slide. Suddenly, I'm first, and that means what I was going to say has to be combined, I think, with a little bit of a general introduction to the issue of mass ejection in planetary nebulae. So that's what this talk is all about. In particular, we're going to look at a subclass of very propitious objects, the bipolar planetary nebulae associated with symbiotics. And we're going to ask the question, to what extent do they help us understand common envelope and evolution? Now, this whole topic, everything we're going to talk about in this meeting is really in a state of flux, rapid progress, but it's difficult to stand back and ask, what do we have to be doing as a community? And the answer is always the interplay between observations and theory. The observations are crucial for validation of ideas, separating the wheat from the chaff, basically. And this class of objects that I'm going to talk about, the bipolars around symbiotic stars, I think is a good place to start, particularly since we know that these objects are closely orbiting binary stars with an AGB Myra donor. What could be better than that? They're big, which means they're easy to resolve. They've got very high speeds. Their ages are 1,000 years if you go by the expansion ages. And one of them is even 200 parsecs away from us. Right? They all come with a lot of data, right? We know about a dozen of them. All of them have hollow lobes. All of them have low central extinction, which I think is a warning that they may not have disks, in which case maybe these aren't common envelope outcomes. Almost all of these objects have a wealth of great data, and all are surrounded by old AGB winds, right, which we can use to see what happens as the flow comes out. The flow is going to have to batter its way through this envelope, and at the very least create shocks. Now, here is a sample of the objects. And let me remind you that what we've heard about in Ursula's introduction and the questions that follow all takes place within one HST pixel and within 10 years. So when we talk about observations, we're always talking about something that happens after the actual event, except in the time domain. Anyway, here's what these things look like. They're very, very symmetric. The stars are bright and they're cool and they're easy to study. Stellar spectrum might be revealing about outflows. And all of them are consistent with former CEE events or accretion jets. It's hard to tell by looking at the picture what put the lobes out there. All right, now I think most of what's in, well, let me go through this. This slide is really something I would talk about in a planetary nebula audience, but here's what are characteristic of this class of objects. The lobes are droplet or bowl shaped. They're round. They don't have straight edges. You never see anything on the inside, with possibly one exception that I'll come back to, and which is the reason I signed up to give this talk. The edges of the lobes are very sharply defined, which almost certainly means something is pushing on them like a wind, or has been pushing on them, and the thermal pressure hasn't broadened them. I think that's unlikely. The temperatures in the edges are going to be 10,000, the equivalent of 10,000 degrees. That the expansion speed is about 10 kilometers a second. And if the winds weren't pushing on them, these edges would have melted by now. The edges expand at 100 to 300 kilometers a second. So if anything is blowing on them, the speed of that would be that invisible wind in the interior, is even faster. About half of these objects have little things in the middle. They're nested structures in the first four cases here. And that tells us that there's a recurrence which may or may not be consistent with any sort of a common envelope. When a common envelope's ejected, I would think that's the end of it. The envelope is gone. I could be wrong about that, and there could be a second episode as the companion falls in further. I don't understand how that would work. All of these things are characterized by homologous growth, that is uniform growth, or what people in the planetary field used to call Hubble law flows. The expansion is proportional to radius. The easiest interpretation, but not necessarily the right one, is that these things are expanding ballistically, in which case you get an age. All right, now I don't think I had to spend much time with this audience on this slide, but there are winds coming out of the star. They're collimated. If they're not tapered, that is, if the wind momentum, flux, and speed within a cone, within the collimation cone, don't change with latitude, then this is what you're going to get. The lobes will all look like this, partly because this diverging flow is flowing into an AGB wind, which itself is diverging spherically. So this is what the outcomes of the lobe should be, and you don't even see anything close to that. Tapered flows, on the other hand, have a changing momentum, flux, and speed with latitude, right? And with that, you're going to get curved lobes just because the momentum flux is non-uniform in polar angle. And the flow, if it's low density, what Noam calls light, will be lead to hollow lobes surrounded by walls which have been displaced and compressed by the wind and shock. And in these cases, you expect to get lobes that look like this. And then, that's more or less what we see. Now, all these properties, the ones back here, these guys, have been discussed in the planetary nebula community. And it's really this last one which has been contentious. And there's one explanation for all of these attributes of the lobes, and that is a turbulent collimated flow. So there have been lab studies of flows like this one. This is a heavy flow. The density here is much heavier than the surrounding, and I couldn't find an image of a light flow in the lab. But I think the general attributes are going to be the same. All you have to do is have a turbulent flow that breaks off a jet, and you get a tapering. This is the speed tapering as a function of polar angle, and it's Gaussian-like. And the speed up the center line in these lab studies increases linearly. So this ticks off a lot of the boxes in the slide that I showed previously. It provides some sort of a framework for understanding what goes on. The hollow lobe interiors, that comes about because we assume the flow is light, lower density than its surroundings. You get the teardrop-shaped lobes. You get self-similar growth, and you would expect to get, at least for light flows, a strong shock spectrum or emission around the edges where the streamlines slam into the material that they've already displaced. These attributes come from this paper, which took me forever to find. Now we turn from a discussion of a general discussion of what symbiotic bipolar planetaries look like. And let's go into some case studies. Let's take a look and see if the flows are turbulent. And here are some examples of models which have been produced in the recent past. This one is by Amy Zhao. So in the interest of full disclosure, I'm a co-author of that, but all this work was really done without me. She considered a variety of cases of common envelope outcomes. This is a sample at a particular time, it's a sample when the length of the longest lobe reaches about 100 AU.
2 minutes, Bruce. 2 minutes.
Okay. This takes a few years, not a few thousand years. YSO accretion disks have the same turbulent flows. There are some examples of what are clearly eruptive events like Eta Carina. Eta Carina has counterparts in the symbiotic bipolar nebula community, this one, but it isn't, what we see here just has a physical resemblance to it. That is, the collimation of the winds has got to be similar, but whether this is the result of a sustained wind or an eruption, it just isn't clear from the image, nor is it clear from the kinematics that have been published on this. I think this is a very special case and an interesting case, because in this case, the ionization structure shows that the highest ionization lines lie further from the star, that's the blue, O3, than the red, which is nitrogen 2. There are ionization zones both in the inner hourglass and in the outer hourglass. So photoionization just isn't relevant here. And the simplest explanation, I won't go into the details, is shock ionization from a sustained wind. It has to be sustained because the recombination times out here are relatively short. This is really the highlight of the talk, our Aquarius. It has, there's an image that is, there it comes. What you see here is buried inside the walls of a lobe, which don't extend out they're not visible very far out. Although here again, the oxygen 3 lies further from the center than the nitrogen 2. Our interest should be on this jet. This is an X-ray image from Chandra, and the jet is obviously hot, and by that I mean well over 10 to the 6 degrees, which means the flow speed of whatever is heating this has got to be 100 kilometers a second or more. Now, I've taken a series of HST images that I found in the archives, separated by 3 years. What a perfect series. And I studied the jet, the orientation and properties of the jet, and you can see that it wiggles, right? It's not, whatever's ejecting of this thing is precessing or changing its orientation, which I suspect means it's unlikely that this jet comes from a common envelope of any sort. The jet was discovered back in 1934, so it's not young. It's been doing its thing for 50 years or almost 100 years at least. There are proper motions in here. The arrows are supposed to show you things that move, and I can't go into the details, but the ages of the kinematic ages are a few hundred years. Now, I made a movie out of the 3 images that show the outer lobes, and this is the first time we've ever seen emission coming from inside a lobe, inside a lobe. There's no doubt that it's expanding. There's no doubt that there's a lot of turbulence going on. I mean, vortices and features are changing shape. It's a little bit difficult to calculate proper motions because the motions are so irregular. But still, you come up with motion speeds which increase with radius, as you would expect them to in a turbulent flow, right? And they get up to about 300 kilometers a second. This slide, there isn't time, but if you follow the little blue lines, which you can when this talk comes out later, you can more carefully take a look at the proper motions. Now, I found this interesting set of analogies just by screwing around playing with the web. You get, this is a flamethrower, and for some reason it's changing its colors. The structure in the flamethrower is not unlike that in the lobe. Now, in this case, there's a flamethrower that's driven by thermal and ram pressure, and the gas is igniting here. And then in the outer lobe, the pressure of the thermal pressure seems to go to dominate, and you get something which looks like the lobes of our Aquarius. So that places me just about at the end of my talk. Here's the bottom line. These easily studied visible symbiotic bipolar nebulae don't show any evidence of having undergone a CEE, at least not yet, or not in the recent past. They're better suited for studies of accretion disks or the jets that flow from accretion disks. That's the bottom line, and that's why this talk really doesn't belong in a meeting on common envelopes. That wasn't clear going in, but I think that's the direction that the evidence points. One last slide, and one thing I have been appreciative of throughout my entire career is this AGB newsletter, a labor of love by people at Manchester. It's the tie that binds us all together. This is the easy way to discover papers in fields not only in your own area of interest, but in closely related areas of interest. It has been a fabulous resource, and I owe them a big round of applause. I am finished.
Okay, thank you, Bruce. We already have some questions. Adam, I think you were first.
Bruce, I'm sorry. I just a clarification. What's the orbital period of our Aquarius?
The orbital period is about 40 years. Well, it's a complicated system. The shortest orbital period is about 40 years.
And the precession of the jet, is that 40 years?
Well, we haven't been able to follow it continuously for long enough to really definitively answer that question. There's a recent paper by Limas et al., which appeared in 2018, which pursues that question. They took about 25 years worth of images. And to be honest, I don't recall what they found. Maybe somebody here can answer.
Yeah, so I'm a co-author on that paper, so maybe
yes.
I can
say something. Beautiful paper.
Yeah, Tina did great work. The issue is that the flows that you see, as the further out you get, become more and more complicated, and it's not just the flow from the jet, but you also start to see like superluminal motions, which are due to not true motions of knots or jets in the jets, but rather through transversal shocks and illumination effects. So really, you can only trace the movement of the jet with this data that Bruce is showing you, where you can probe it on these very short, very small sub-arc second scales. Whereas the data that we have, the ground-based data that we have, is very good at probing the properties of the more extended lobes, but not in terms of probing the precession velocity of the actual jet.
No, you did it. Yeah, no, as I recall, you estimated expansion ages for the individual elements within the jet of 100 to 300 years.
Yeah, exactly.
Yeah.
But so is there at least an estimate for the precession timescale? Is it of order of that orbital period?
Yeah, like Bruce says, of 40, 50 years, something like that.
Thank you.
So I think Laura is next.
Yeah, I was wondering if you have a mental model for why some symbiotic systems show these big extended jets and others don't.
No. I mean, there's a flippant answer, and basically it's the structure of the wind and the speed of the wind that emerges. Now, all these lobes are expanding highly supersonically, at least compared to the sound speed of a 10,000 degree gas. That's 10 kilometers a second. And the lobes themselves, the Doppler motions and the proper motions, are way beyond that. So supersonic flows create structures which are pretty much fully determined by the properties of the collimated flow at the nozzle, especially if they're light.
Right. Well, so why do you think some symbiotics have such collimated flows? Because I think in other cases, I think in almost all symbiotics, the nebula looks bipolar on some level, but I think it's this very highly collimated flow that there in some and not others.
Laura, there are 36 symbiotics known in a paper that I found in 1980. I mean, it's a long list. The lobes are found in only a dozen of these things. So symbiotics may have piles and piles of flows which don't have any observable consequences. It's hard to tell. You can't conclude anything on information that you can't see.
Well, I have a question that sort of builds on that maybe is not a nice question, but are these planetary nebulae or are they symbiotic nebulae? Meaning, where does the material, is it material that was ejected from the Post AGB star, or is it material that's come from the envelope of the companion of the AGB star? And does that impact on the results?
I think it's pretty clear that only the orbital angular momentum could propel the flow. How that works is beyond me. You have to be paid more than I am, and I'm retired.
Okay, so then maybe we have time for one more question, Steve.
Well, there might be a system that could help here, even though it's a freak, SS433, because there you have a light jet and also a disk wind that's clearly collimated, but not anywhere near as collimated. That's evaporating off of the extended disk, so well outside the hole.
Yeah.
And in that case, you can actually trace the individual structures. So the one thing I wanted to mention, Bruce, is that if you've got a light jet, then you're also going to have coherent structures that are generated, which you don't have in the heavy jet case. And the entrainment of the boundary is going to be different. So you might be seeing these blobs moving outward and at the same time also changing their ionization because of changes in the central source that you would be able to trace, but are not necessarily the actual velocity of the jet.
I think I understand what you're saying. You and I can talk about that offline.
Yeah, I'd love to.
SS433 is, I think, evaporation flows are another class of bipolar nebulae, right? Planetary nebulae with bipolar shapes are not just those from symbiotics. There are a bunch of really powerful, beautiful ones, powered by really massive stars, or what were massive stars for planetaries at the center. Most of these objects have stellar central temperatures of 100,000 degrees or thereabouts. So they're not coming from Miras, they're not coming from symbiotics, they're bipolars, but their origins, I think, follow a very different evolutionary path. And Joel Kastner and Adam and I and others have papers coming out on these.
So in the chat, we have a clarification from Miguel, who says that the symbiotic nebula comes from the fact that material of the nebula is coming from the giant, not from the hot companion. So maybe this is a clarification on my question, where if it was a planetary, you expect the material to be material which was previously ejected from the AGBs, from the post AGB star or the white dwarf, right. Whereas in a symbiotic, the material itself is from the wind of the giant.
The original material that is ejected very slowly from the AGB wind, and then the jets from the companion or the something going on in the orbital system ram their way through it to form the lobes.
Yeah.
So the edges of the lobes are old AGB material that had been displaced and compressed by the high-speed flow coming from wherever it comes from.
And then finally, from the Slack, Jesus mentions that NGC 2392 has a nice roundish inner cavity with an amazing ongoing jet piercing through it. Is it a symbiotic? I would say no, because in that case, the orbital period there is less than 2 days. So really, you can't have an AGB companion where the majority of the material is coming from the.
In addition to that, there's a lot of doubly ionized helium in that nebula, which requires a star with a central temperature far beyond that of a Mira or an AGB star.
Okay, so I think we can move on to the next talk. Thanks again, Bruce.
Mm-hmm.
So if you would stop sharing, please.
Something. There we go. So I'm
there
sorry.
We go, thanks. The next talk in this session is from Aka Corporal, who will talk to us a little bit about these Van Winkle systems that we've mentioned so much already. Please, Aka.
So I assume you can hear me and you can see my slides?
Yes, perfect. Thank you.
Thank you, Dave. Thanks for the organizers for giving me the opportunity to speak at this conference. In collaboration with these people, I'm studying the disks that are formed around Post AGB binary systems, and I'm using infrared multi-wavelength interferometric observations. The Post AGB star is an evolved Lonza intermediate mass star, which is in a luminous but rapid phase between the AGB and the planetary nebula. Half of the stars in this mass range are found in binary systems. When the initially more massive star has evolved to the post-AGB phase and the companion star is still in its main sequence phase, the system is said to be a post-AGB binary system. And when we look at these systems with photometry, we almost always see an infrared excess in the spectral energy distribution. And this can be attributed to the presence of a circumbinary disk. The presence of such disks is really strongly linked with the binarity of these systems. It's now well established that these disks are stable and that they are in Keplerian rotation. The post-AGB binary systems are binary interaction products, but they have likely avoided a common envelope evolution. The expected strong phase of interaction may not have happened or have happened in a different way that we think it has happened. The one discrepancy that we see between the observed and the predicted orbital properties, there's a discrepancy between the observed and the predicted orbital properties of these systems. From theory, we expect that the outcome of common envelope evolution may have either been short period binaries or long period binaries. On the one hand, systems that underwent a common envelope evolution are expected to have spiraled in considerably due to friction between the stellar cores and the common envelope. And on the other hand, wider systems are not expected to have interacted significantly, and they are supposed to get larger orbits because of an isotropic stellar wind of the AGB star. But what we observe are periods that fall in between these categories. Observed periods range from about 100 to a few thousand days. Also, the eccentricities do not match what we predict as the outcome of the common envelope evolutions. The eccentricities are expected to be zero because of tidal forces on short timescales, but we see a lot of post-AGB binary systems that have significant eccentricities, even up to a 0.7. A picture that arises now is that these orbits are too small to have accommodated a full-grown AGB star. So they have likely avoided the common envelope evolution, but it can also be that the common envelope has been expelled very efficiently. One thing that makes these systems also interesting is that these disks around evolved binary systems are in many ways similar to protoplanetary disks around young stars. Therefore, they can be seen as a laboratory to probe the formation of microstructures and maybe even second-generation planet formation. The previous binary interactions have resulted in complex systems, and this sketch shows the building blocks we are dealing with. We have a post-AGB star, and its likely main sequence companion. The main sequence star is surrounded by an accretion disk from which some bipolar jets are launched. And if you want to know more about these jets, I encourage you to tune in for the talk of Hans van Winkel on Friday. But in this talk, I want to focus on the massive circumbinary disk. And this disk has likely been formed somewhere in the interaction processes between the two stars, but the exact formation processes are unknown. Studying this disk is interesting because it has an influence on the evolution of the binary system. Because we see a continuous interaction between the circumbinary disk and the central binary. These systems are located relatively far away at distance of about 1 kiloparsec. And therefore, the apparent size on the sky is small. In order to see the details, mainly of the disk I'm talking about now, we need high angular resolution observations. And this sketch shows with which observational technique we can study which part of the disk. With near-infrared interferometry, we can study the hot optically dust inner rim. While with mid-infrared interferometry, we can probe beyond the dust inner rim, maybe even within the planet-forming region. With ALMA in the radio, we can probe the global structure of the disk. And with adaptive optics, we can probe the outer surface layers of the outer disk. But in this talk, I want to focus on infrared interferometric techniques, with which we can probe the very inner regions of these disks. To explore the potential of multi-wavelength infrared interferometry, we've taken our rich data set, which was taken with all current Very Large Telescope interferometer instruments, Pioneer, Gravity, and Matisse. For the first time, we combined these three instruments to analyze the data. So these instruments are operating in a range of wavelengths. And in this wavelength regimes, the SED shifts from a star-dominated regime in the near-infrared to a disk-dominated regime in the mid-infrared. So all data has been taken with the 4 movable telescopes on the VLTI. And in all configurations, and with that we have resolutions in the CPU scale. And in the next part of the presentation, I will use the visibility as an observable. Visibility is one of the interferometric observables, and it is the normalized amplitude of the Fourier transform of the brightness distribution on the sky. In other words, it is the contrast between the fringes as a function of the spatial frequency. And the spatial frequency in the UV plane, so this is also absorbed in the baseline length that I will show now. So we fitted geometric models to the data, and this is shown in here. So we have data in 4 bands. We have fitted best fitting models in these 4 bands as a visibility as a function of the baseline. It can be seen that the model fits the visibility data generally very well. It fits the overall shape of the visibilities quite well. However, not all data points are fitted equally well. So this means that, fortunately, the physics that is happening in the circumbinary disk is more complex than the physics in the geometric models. It's also a bit important to notice that the visibility can be used as a probe for the radial structure. So I'm not talking about the azimuthal or the vertical structure here, no. The images in this lower panel show the images of the best fitting geometric models of each individual band. It can be seen that in the mid-infrared, the emission is more extended compared to the near-infrared. This means that we are really probing a disk and we're not probing only a shell of dust. You also may notice that these images in the near-infrared look not equally similar to the images in the mid-infrared. And this is because we use families of geometric models to fit the data. We tried to fit the data of each individual band using both a single temperature ring and a temperature gradient model. From the statistics, the single temperature ring was found to be better represented in the near-infrared data, while in the mid-infrared, we found that the temperature gradient model was fitting better. On top, I show the radial cuts through the center of these images. It shows also the geometry of the two different models. And because in the near-infrared, the single temperature ring fits better, while in the near-infrared, probing beyond the inner rim, the temperature gradient fits better, we can say something important about the structure of the inner rim of the disk. But this needs a bit of explanation. So the SED of the target tells us that about 30% of the energy that is emitted by the Post AGB star is captured by the disk. In order to achieve this, the disk needs to be vertically extended somewhere. But because of our finding that in the mid-infrared, the temperature gradient model fits better, while in the near-infrared, probing really the inner rim, the ring model fits better, we postulate that the vertical structure is at the disk inner rim. And we interpreted this, that the inner rim has a similar shape as what is usually found in young star objects, that it has a rounded or a curved inner rim rather than a wall. So in order to not only model the disks using geometric models, so include more physics because not all data points are fitted, we can model these disks with 3D radiator transfer codes. This will not only constrain the radial direction, but also the azimuthal and the vertical structure.
2 minutes.
Thank you. So the goal of this current research is that using the same data and the SED, that we can constrain the disk parameters in such a way that that one model fits simultaneously all data, so the interferometric data and the SED. And I'm showing here some very preliminary results. So I'm showing here the images of the different bands and the SED fitting for only one model for each band. So I remove here the central stars. So stay tuned for more updates on this. And this brings me to the conclusions. The Post AGB binary systems are complex systems, and they have likely avoided a common envelope evolution. But I also hope that I convinced you that studying the circumbinary disk is really important in order to understand the orbital evolution of the central stars. But that there are still a lot of open questions that have to be answered. Using infrared interferometric data in different bands, we could constrain that the circumbinary disk of one Post AGB star has a puffed up rounded inner rim. And currently I'm working to constrain the disk parameters even more and by including physics using radiative transfer analysis. But we can not only use multi-wavelength infrared interferometry for studying circumbinary disk around evolved stars, but we can also use these for studying disks around young stars or around white dwarfs. And with that, I would like to thank you.
Excellent talk, thank you. So questions, I see Bruce, you have your hand up. You are muted if you are trying to talk, Bruce.
Thank you. I appreciate that. Aka, I have a very simple question. Why don't your portrayals of the disk show any evidence of elongation or projection? That is, you portray them as one-dimensional objects when surely they're two-dimensional and inclined at least to some degree.
Yeah, we incline the disk. So the position angle and the inclination are incorporated in the models, but indeed it's 1D. So we are now using these. Yeah, this was one way to check if we can use indeed multi-wavelength infrared interferometry, so the 4 beam combiners that are currently on the VLTI, in order to study the disk. So this was one simple analysis, and multi-wavelength interferometry works. So now we can do more complicated physics using radiative transfer in 3D.
Thank you. And do you get any information on the disk thickness from the visibility function?
Not directly. No, it's not directly.
Thank you.
Okay, Åsa?
Thank you, Ake. That was great. These objects never really stop to amaze me. One of the reasons is that there's so many quantities that are measured. And while often classes of objects diverge, the moment you think you've got a quantity that's the same for all, then you find another bunch that are a bit different. But these objects are very homogeneous in some ways. And one thing I discovered when Dylan was in Australia was that the companions of these objects have approximately 1 solar mass. Now, these are very heavy companions compared to the post-common envelope main sequence companions, what we're used to in planetary nebula, for example, that tend to be, I don't know, 0.5, 0.4. And so that tells us that somehow these things have kind of equal mass at the time of interaction. And that tells us that the mass transfer may have been more stable than a common envelope typical instability. So the question is whether that fact has to do with the weird common envelope that they went through, or the avoidance of the common envelope. Whatever it is that they did, they've certainly had some strong, crazy interaction that ended up in something different. So I don't know, Ake, if you have an opinion on the fact these are equal mass interacting binaries, and whether that may have played a role.
Yeah, I'm not 100% sure. So they are they then equal mass at the time of interaction? So when the AGB starts, so when the now post AGB, but the evolved star is already in the AGB phase.
That's right. So at the time of interaction, so the post AGB star now is about half that mass because it lost a bunch. Yeah. But at the time of interaction, these are typically. I mean, it's not easy to have stable mass transfer when one star is a big bubbly AGB star, and so there's some kind of mode of mass transfer that is at the edge of what we call stability or instability. So maybe that has something to do with their weirdness.
Yeah, but then we need to study really that interaction between these stars, and maybe they have those orbits already at the time when they are supposed to interact. We also have no idea how such a system arises, or not completely. We don't know the details. We have only ideas. So, do I have an opinion on this? Yeah, I'm not sure. I've never thought about it maybe in that way directly, but I think that indeed the difference in normal common envelope evolution has to do, and common envelope ND system has to do with that indeed. But I don't know if you can observe this.
Maybe along a similar line. Do we know how much mass is in the disk?
It's about 2 times 10 to the minus 3 solar masses. Okay, but so we don't. This for this system. But I think for 2 systems we know that's about similar. So we have 3 systems that, significant.
So there's still a lot of the envelope that is somewhere else. It's not all in that disk. Yeah. The post AGBs AGB envelope is somewhere else. Any more questions? If not, I think I will thank you again, Aka. It was a great talk. And I think that brings this session to a close. Noam and Tomek, do you have anything to say?
It's up to you if you want to have now some small discussion or to leave all the discussion to the end of the session. It's up to you. So, because your session continue after 1 hour break. 55
Well, I think
minutes.
we've already had, unless anybody else has something to contribute, I think a lot of the discussion has been built into these questions. No, I've allowed more than 4 minutes for questions every time, I think. So.
Okay, good. So we stop now for 55 minutes and then we meet again. Okay?
Okay.
Good.
See you in an hour, everybody.